Up until this point with differentiation, we have been differentiating functions of x, where y was explicitly isolated, where y was alone on one side of the equation. So in general, if we wanted to differentiate some function where y wasn't alone, we would try to isolate y in order to differentiate. However, sometimes it's just not possible to get y by itself. Sometimes it's easier to just differentiate the equation exactly the way that it looks. So the functions that we have dealt with so far that have been expressed as one variable explicitly in terms of another variable, for instance, y equals x squared, or y equals 3x squared minus 7x plus 5, any of these are explicit functions of x. However, some functions are defined implicitly by just showing a relationship between x and y where we're implying that y happens to be a function of x. So to find the derivative of a function like this, we're still differentiating with respect to x. The only difference is that when you see terms with only x, we differentiate as normal, but if we see terms involving y, we differentiate as normal, but multiply by an additional dy dx. Since we're implying that y is a function of x, we're actually applying the chain rule. So notice that if there's ever a term with y, let's say we're taking d dx of y squared, which we will do shortly, the derivative will be 2y, but we multiply by an extra dy dx. So an equation doesn't need to be a function in order to find the slope of a tangent line at any point, which we call a derivative. We could actually take the derivative of any equation that's any sort of relationship between x and y. However, in order to find the slope of the tangent line, we can't just use the single x coordinate. We need to know both the x and the y coordinate. So let's take a look at a couple of different types of equations. So some equations can be explicitly solved for y, and are often easier to differentiate if we do solve for y first. For instance, this equation right here. Y is not alone. But if I were to divide both sides by x, we find that y is equal to 1 over x, and we can now differentiate that by using the power rule. But notice as well that this function, that this equation represents a function, since every input gives me exactly one output. But what about this equation right here? Some equations can be solved for y, but are easier to differentiate if we just leave them the way they are. For instance, this circle equation. Now I could shift that x squared to the other side and take the square root, and we actually get plus or minus the square root of 9 minus x squared. Notice that these two functions separately, the positive and the negative, are functions of x, the positive being the top half of the circle, the negative being the bottom half of the circle. But it turns out that it's not necessary to isolate y in order to find the slope of a tangent line. What we are going to need, however, though, is the x and y point if we want to find the slope of a tangent line. Because if I only choose the x coordinate, I don't know if I'm referring to the point on the top or to the point on the bottom. But then again, there's some equations that simply can't be explicitly solved for y. And there's no other way to differentiate them than by the process of implicit differentiation that we're about to learn. For instance, this equation that has this particular graph. Notice that it's not a function since it doesn't pass the vertical line test, since every x doesn't give exactly one y. But it doesn't mean that we can't find the slope of the tangent line at any location. The problem is we can't actually get y by itself. What if we look at an even crazier equation, something like this one that involves exponentials and trigonometric functions and even a trig function with an x and a y inside? It's going to be impossible to isolate y for this. And it would also be impossible to be able to draw this graph in order to find out what the slope of the tangent line is. But what we can do instead, even though we can't isolate y directly, is we are going to be able to apply implicit differentiation. So let's look at an example about how to apply this process. Although this equation right here could be isolated for y, we're going to assume that we can't do that, and we're just going to leave it as is. And we'd like to find dy dx, or the derivative of y with respect to x. Now think about what that symbol means. It's saying the derivative of the function named y where the variable is x. Well, we don't see explicitly what y function we're referring to. But we are implying that y is a function of x, and if I solve for y, it would be a function of x. So how do we find the derivative? Well, we do the exact same thing we've done before. We differentiate both sides with respect to x. Now on the left side, notice that it's a product between two functions. X is one function, y squared is another function, so we must have to apply the product rule. Now we're going to write the actual symbol ddx before we differentiate. So I'm going to list out that this is the first function times the derivative of the second function plus the second function times the derivative of the first function. And notice that on the opposite side, the derivative of 2 is simply 0. Well, now let's take a look at this ddx of y squared. If we apply the chain rule to this, assuming that y is a function of x, then we should just have to apply the derivative of the outside, which is 2y, times the derivative of the inside. So if we ever differentiate a term with y, we're simply going to multiply by an additional dy dx. Let's think about why that happens. This is all because of the chain rule. The derivative of y squared is 2y, but because we're differentiating with respect to x, we have to also multiply by the derivative of the inside function, which is the derivative of y, or dy dx. But notice over here, ddx of x is simply 1. We don't have to multiply by anything additional. And therefore, if I now try to isolate dy dx, all we're doing at this point is shifting y squared onto the right side by subtracting. And then we divide by x times 2y, or 2xy. One of the y's cancels. And notice that by isolating dy dx, we get an equation for the slope. Now this should be interesting because notice that if my equation, my original equation, was in terms of x's and y's, then the equation describing the slope is also in terms of two variables. It now implies that we're going to need both an x-coordinate and a y-coordinate to find the slope. So if I want to find the slope at 2, 1, as the problem asked us to do, we simply replace x with 2 and y with 1, and therefore my slope is negative 1/4. So this is a process of implicit differentiation. Why don't we go ahead and take a look at a slightly more complicated problem? How about that equation that we listed on the previous slide? First things first here, we want to differentiate both sides by taking ddx of both sides. Now we need to pay attention to what rules we have to do on the left and the right. Here we have a product of two functions, e to the y times cosine x. While on the right side, the derivative of 1 is 0, but now we're taking sine of xy, so we have to apply the chain rule here. So when we apply the product rule to the left, we get the first, e to the y, times the derivative of the second, ddx of cosine x, plus cosine x times the derivative of the first, ddx of e to the y. And now the derivative of 1 is 0, plus the derivative of sine of xy. Well, again, by the chain rule, we take the derivative of the outside function. The derivative of sine u is cosine u, keeping u intact, times the derivative of xy. So now we've got to realize that we've got three different derivatives that we now have to find. ddx of cosine x is a pretty simple one because notice that it's just a function of x. So that simply becomes negative sine x. For the second one, ddx of e to the y, notice that this is now going to apply the chain rule, or implicit differentiation. ddx of e to the y is e to the y. times the derivative of y with respect to x, which is why we multiply by an additional dy dx. And now we have cosine of xy times the derivative of xy. Now be careful with this one because we have to apply the product rule here as well. Since this is a function of x times a function y. So we get the first x times the derivative of the second. The derivative of y is 1 dy dx. Now for the second part of the product rule, plus the second function, which is y, times the derivative of the first. We now just simplify by using a little bit of algebra here. We're going to distribute the negative out in front here. Here we get e to the y cosine x dy dx, so we just got rid of the parentheses. And over on the right side, we're going to distribute the cosine xy to each of these terms, therefore giving me this quantity on the right. Now you should realize that there's a few terms that have dy dx and a few terms that don't have dy dx. So we're going to shift the dy dx terms onto the left side, and we're going to shift the non-dy dx terms over to the other side. So we shifted x cosine xy dy dx onto the left, and then we added onto the right e to the y times sine x. Well, we're about done because now notice both of these terms have a dy dx, so we factor out the dy dx, and when I divide both sides by the remaining quantity, I now get an equation describing the slope of the tangent line at any point xy. So yeah, this is definitely a complicated derivative. It's a lot easier than applying the difference quotient. And not only that, if we didn't know implicit differentiation, we would have had to find some way to isolate y, and that would have been, if not impossible, very, very challenging to do. So in getting used to implicit differentiation, the main thing we have to recognize is anytime we differentiate a term that happens to involve y, we just multiply by an additional dy dx.